Welcome to Harnessing AI for this week. This week our topic's going to be natural language and AI. So natural language is referring to the way we all speak to each other, the way we use language naturally. And this is a topic it's been of great interest for many, many, many years. Back when I was still a undergraduate student, I remember visiting Bell Labs, and they were trying to do speech synthesis there. So they would take texts and see if they could get a mechanical voice to read the text. At that time, those things sounded pretty awful. They sounded like robots, but I guess for blind people who couldn't read books, they were very, very helpful. One of our colleagues, Ray Kurzweil, some of you know that name, is the guy who predicted in his book the singularity, the coming singularity, which Professor Rowe talked about a little bit last time. He started his work in that area, using speech, trying to read texts and help people who couldn't read by themselves. So there's been a lot of work on reading stuff, listening to speech and turning it into text, listening to speech and translating into another language, translating languages between each other in text. All sorts of things of this type have been studied, and the machines have been getting much better at them over the years. So today our speaker is Professor Neil Rowe, who was here speaking to you a few weeks ago, and he'll talk to you on this topic. He is a pioneer in the AI field. He's been teaching at NPS for over 30 years. In 1988, he authored a book on Prolog, which is one of the perhaps the most famous language in artificial intelligence. And he knows more about artificial intelligence than anyone on campus and probably in the whole universe. So please welcome Professor Rowe.
Okay, great. So one of the goals of AI for a long time has been to deal with human language. And so this has been a big area for a long time of research, as you'd expect. I mean, one of the things that people consider an important aspect of human intelligence is being able to talk with you and say intelligent things. And so people have been trying this for the 60 years in the history of AI, trying to get improvements. And you probably noticed there have been great improvements in speech understanding in the last 10 years in particular. So I wouldn't say that there's been breakthroughs recently. I think what's happening is that as computers have gotten faster, many of the existing algorithms and methods that people have used for natural language understanding have gotten better. There's also an aspect of natural language generation, which Professor Denning alluded to there. I'm not going to talk about that because generally that's more straightforward, how you generate sounds in order to talk with somebody. But the hard part is the understanding of what's said. And it turns out to be more difficult than people thought originally back in the 50s when they first started looking at speech understanding. So the AI term for this area is natural language processing, NLP. And so it's natural languages as opposed to computer languages and processing. But some of the same techniques used for computer languages, like parsers and interpretation, are used also in natural language understanding. So anyway, humans, of course, would love to have natural language AI because that's the easiest way to communicate with computers and devices, right? If you can just talk and have the computer understand what you're doing. The disadvantage has been, though, that the speech that people produce is pretty noisy signal, as I'll show you in a moment, and so there are going to be errors. And trying to get the error rate down has been a key issue. Another issue has been the speed of computers. Back in the 1980s, we had speech understanding systems that you could say something like 5 words long, and a minute later they would figure out what you'd said and respond. So you can't have a conversation when you have to wait a minute for each step in the conversation. So we've gotten to the point now with the speed of computers where we can respond within a second, and that's led to all sorts of new applications that you can probably see today. So the main sort of applications we're talking about communicating with automated systems, We'd like to be able to communicate with all these computers and devices in natural language rather than having to type things in or that are full text and stuff like that, or having to click on a screen and places on the screen in order to do stuff. Summarizing text is also important. There's a lot of material that's created in the form of text, and you can sometimes that's very important. Some things, archival things, often are going to remain in text for quite some time to come, and so we'd like to be able to get some idea when there's something interesting in there. Extracting clues from text. One of the things people do with text is to analyze it as to the speaker's intentions or their nature or something else about them, try to find what's relevant in that. And then translating text. One of the big applications nowadays is trying to translate from one human language to another. So I'll say a few things about that going along. Of course, to translate something into human language, you have to understand it, or at least comprehend it in one language first. And so a lot of the basic things I'm going to talk about are going to be used for translation. So here's some of the areas of research. So we got things like speech understanding, where we're going to listen to a speech signal. Speech is an acoustic wave phenomenon, and so what you need to do is analyze the acoustic properties of the speech signal. Usually what you do is you look at the frequencies. There's some things in the time domain you can look at too. But anyway, you look at this signal, and of course the military has a long history of analyzing signals, and some of that same stuff is relevant to doing speech understanding. The main challenge is to get the speech signal in terms of phonemes, or units of language, the sounds that basically that are supposed to be letters, and pretty much every human language has about 40 phonemes. Turns out that if there are more than 40 phonemes, you start to get them confused with one another. So even though there are all these different languages and they sometimes have some differences in the phonemes, they all tend to have about 40 phonemes. And so that's what you got to figure out for speech understanding, which phonemes somebody used when they were talking. Now, once you've done that, then you got to figure out the words. Pretty much all languages have words, and so you're going to have to figure out how those phonemes go together in words. Surprisingly, if you listen to a speech signal, at least in English, there's no gaps between words. They're usually all strung together, no obvious gaps. Usually there's an obvious gap at the end of a sentence where people pause, but other than that, it's up to to a system that's analyzing it, an AI system. The challenge is to figure out where each word ends and the next one starts. There's also issues with morphology. There are endings on words that are important in some languages. English doesn't have as many as some of the European languages. And then there's things like punctuation. There are ways, if you're dealing with written language, you're going to have to figure out where the punctuation marks are, how they function, stuff like that. Then there's grammar. So grammar or syntax is the structuring that you use for the language. So if you're really going to understand language properly, you're going to have to need to know how the words form an overall structure, and that's called grammar. And so that's one of the things, big traditional areas of linguistics. So there's an area of research called linguistics that's been looking at this long before computers and trying to analyze that. And then semantics, once you figured out the structure of what was said, you need to figure out what its meaning is. And its meaning usually involves the relationships between the words, trying to figure out how all the different words are related to one another. That can be hard. I mean, a lot of it involves looking at a lot of different special cases and trying to accumulate knowledge. So in many ways, it's more like expert systems development than some of the other areas of AI we've talked about in this course. Then discourse analysis. All this stuff I've been talking about so far is focused on the sentence. You also want to look at sequences of sentences, because there are often situations where one sentence sets up the next sentence, and the next sentence explains a consequence or a result of a cause that was in a previous sentence. So all those things are analyzed in an area called discourse analysis, which looks at paragraphs and whole documents and things like that, or whole sentences in a speech, for instance. And then translation, as I say, is sort of a separate area. You're also going to have to know things about how the words in one language map to the words in another language. And it isn't always one-to-one, which makes it more difficult. So, first let me talk about speech understanding. There's, as I say, a lot of progress on it recently. And you see it all the time now in commercial systems like phone call management, where you have to say what extension you want to connect to and things like that, or answer simple questions. It's also used in automatic dictation transcription. There used to be a lot of secretaries that were doing dictation, all the time, and so some of that has been taken over. It's not perfect, but it works for most purposes, and somebody can come in and post-process it or do some editing when it does make mistakes. Now, of course, there are digital interfaces to computers and digital devices like Alexa, Siri, and Google Assistant. So you've probably encountered one of those at some point. They're basically looking for a limited set of things that you could say. If you can limit the number of possible words in the speech, then speech is much more successful. So how many words? Well, if you can limit the number of things somebody could say to 10 things for the next thing they're going to say, at that point you can have some pretty fast algorithms and methods. But if you go from 10 to 100 things, there's going to start to be some errors. And if there's more than 100 things that somebody could say at some point for the next word, then it gets very difficult for speech understanding with the techniques that are being used with things like Alexa, Siri, and Google Assistant. So what's the reason for that? Is they're doing shallow processing. I'm going to distinguish shallow natural language processing, where you just try and pick out the words, from a deeper understanding where you have to figure out how the words go together to form a sentence. So I say most of these techniques were developed 40 years ago. There were some good systems back in the 1970s, but they're just too slow. So finally things became practical as we got these things fast enough. Now, one of the things that's going on with these is that they've got a large database of stuff. Now, oftentimes now with the new systems, though, what they're doing is using a neural net. And so a neural net has been trained on looking at lots of different pronunciations of the words. And so when something new comes in, somebody says something into the system, it finds the closest match to what it's seen previously through this neural net. And this neural net will guide it in the direction of the most likely interpretation. So that works fine, as I say, when you got 10 words or less, say, that you're expecting at some particular point. But you can get better accuracy. If you're going to get better accuracy, you need to know common sequences of words. And so some of the better speech understanding systems will have that defined in advance for the neural net, so they'll recognize those sequences. Then also, if you train for a particular speaker, you can get better performance. So training means that you read some text into the system, and that's been prepared in advance, so it knows what you're trying to say, and then it builds the neural net, or it stores the cases based on those examples that it knows what the correct answer should be. And that works pretty good. Definitely you can boost your performance if you do training. A lot of these online systems, though, for commercial companies where you're just choosing an extension, for instance, a phone extension, they don't need to have that sort of deep training, so they have something sort of just general. That does mean they can make mistakes. Here's an actual speech signal looking at the frequency domain. So seconds is along the horizontal axis here, and then frequency in cycles per second is the horizontal axis. So for understanding speech, people can hear down to about 100 cycles per second, or 100 hertz, and people can hear up to about 10,000 hertz, actually up to 6,000 or 7,000 is sort of a practical limit. So those are the limits of the human ear. That's why the speech is designed for that. So all you have to do is duplicate the acoustical properties of the human ear in order to try to get some good input for a speech understanding system. So this is the spectrogram, as they say, of the word phonetician. So this is the F sound here. This is the O, and then there's an N in here. And then there's a T sound for the titian, and then this is the I, and this is the SH sound from the shun, and then this is the un at the end of the thing there. So that's what it actually looks like. you see there's some vertical bars there, and so what those are the vocal cords flapping away. The way you create sounds is you flap your vocal cords at a relatively low frequency. The vocal cords, their frequency is consistent and they're constant, but it's like an organ pipe. You can get overtones and other sorts of things in the vocal tract because it's quite irregular, and so you can manipulate the shape of your mouth in order to get different frequencies out, and that's what you're getting on these different vowels. Particularly the vowels are the more easy to patterns to see. Here are some vowels. This is the O sound, for instance. And you notice that's different from the sound that's coming over here. So vowels are actually easier to distinguish than consonants, and because there's quite a lot of stuff. In fact, particularly there's some noisy consonants like this F sound for phonetician and the SH sound. You can tell, sort of generally speaking, the F sound has lower frequencies in it than the SH sound over here. But that's kind of a weak clue. That's one of the reasons that the languages don't have any more than 40 phonemes, because there are too many of these sounds that just look too close to one another to distinguish them easily. So anyway, so that's what it looks like and what we're up against. So that means that you can't do this in a sequential processing. You can't do speech understanding sequentially. Well, you first figure out the phonemes, then the words, then the sentences, and so on. You're going to have some guesses as to what the words are based on this, then go back and look at the speech signal, see if you can find evidence to support those words. So that's what a good neural net can do, basically. So you can do some things like that with a neural net. But it does involve more than just looking at the speech signal in order to get progress on understanding what was said. So that's an example. For the most part, you can do shallow processing. And some other examples of shallow processing, you could recognize words from a small set of possibilities, like spoken numbers. You've seen probably a lot of phone services ask you to recite numbers, and so they got 10 digits, right? And they learn to recognize those types of things. I can also find text matching some keywords. That's what Google does, right? It stores lots of indexes on different words and stores them in it. And so that's a shallow processing technique because Google doesn't understand what those words mean. It just knows that they tend to occur in particular documents and uses that to help you look things up. Then you could classify some text, another shallow processing thing. For instance, recognizing spam is one great success of this. One of the weaknesses of spam, we used to have a problem 15 years ago or so with spam, and it's greatly decreased since then. And the main problem is if you're a spammer, there are certain words that you need to use in order to get people to do things, like the word now, or other words that suggest urgency, like your computer is in terrible danger, you're going to have to fix your computer. And then there are certain products that everybody wants, like Viagra, for instance. So you can look for those words then. If you try to be too unclear about it in order to avoid the spam checking, you're not going to be able to sell anything that way. So the spammers are losing the war at this point. They're not perfect, though, because there are new types of spamming. And then, of course, there's phishing and spear phishing that we have to worry about, where something is targeted in a more direct way. But spamming, per se, is going to be difficult. So we're getting 99% success rate on recognizing spam these days. Authors. One thing the intelligence community is really interested in is tracking terrorists. And so you can find out by looking at their text who has written the same documents. And so that's actually been an important application of things. You can also do that with speech. See if you can listen in on phone calls and see who's talking too. Again, that depends on individual words. You can look for individual words and often they'll give you a clue. Emotions. I was talking about emotions last time as being an area of AI which is actually easier to deal with than some people think. So you could recognize when somebody is angry. When somebody's angry in text or in a blog, they're going to use particular words, and you can learn statistically what words associate with a person being angry. You can take some text which somebody has labeled, and somebody will label the angry text, and some label some non-angry text, and you can learn what words tend to be used more often in the angry text than the non-angry text. So lots and lots of projects going on like that, looking for trying to detect emotions in text of one sort. And one area I've been particularly interested in is deception. My cyber deception book talks about some different ways to detect deception. And one of the things you can do in text is actually look for certain types of words. And I'll show you some examples coming up. Now another thing you can do with shallow processing, you look for co-located words. I was just at an AI conference with lots and lots of Chinese. It was scary how many Chinese were at this AI conference. So some of them were doing co-location. They were basically trying to figure out what words tended associated with other words. And that can give you often a theory of what things tend to be related in the real world. And if things are related, you can maybe do some stuff like that. For instance, in advertising, Google likes to know what words that when people are looking for a product, they also use at the same time. And that could maybe suggest other products that could be advertised to them and things like that. So co-location is a key to maybe getting some clues as to how words relate to one another, clues to semantics and things like that. And then shallow processing, there are some deeper approaches to translation, but there's a shallow approach to translation used by Google Translate, which I'll talk about in a moment, which uses previous translation of parts of text and combines them, glues them together to make a translation of an overall text. So here's some deception clues from a paper a while ago. So they did a study of documents, some of which involved deception, some which did not involve deception. And they found when people were deceiving, they used first person less often. So they used the word I, we, and stuff like that because that might suggest they were doing something that was just their perspective that might involve deception. Also, there was decreased use when they were deceiving of except, unless, without, and however. So again, what they do is they just count up the number of times those words are being used in deceptive text and compare it with their rate in non-deceptive text. And that works really good. What you need to do, though, is look at a bunch of different words, because any one word is not going to just tell you if you've got deception or not. Then also, interestingly, those first two clues were pretty good. Then they were basically negative clues, but there were also positive clues, like if somebody uses the word hate or dislike or ignore, that was a clue to deception. And then if they used action verbs like move, go, and carry, that turned out to be a positive clue too. So interesting. Sometimes you discover surprises when you analyze the strength of different types of clues. I did a project where I was looking for captions on the internet, and captions are not often labeled clearly. So what I had to do was look at the words of the caption. So I came up eventually with a list of 150 words, either positive or negative clues that were good at indicating whether something was a caption or not. So you can build a lot of simple systems this way that are quite powerful. Here's an example I'm going to use. Chinese powerboat reported 30 north, 70 east at 1300 heading east at 20 knots leaking oil. And so Google could index all those words there and try to give us some information about them. We can index all the important words. Any words that are relatively rare in English are going to have more value. So that's one of the key principles that people learned in doing this shallow processing. You look for the things that are rare as indicators of what sort of special characteristics you have that you could exploit here. We'd also have to know that this is a position here. It does say at, and it doesn't look too much like a time, so we'll probably guess it's some sort of location. One of the problems in English is that prepositions like the word at have multiple meanings, quite a few different meanings, and so we're going to have to figure out which of those meanings there are in context if you really want to do it right. In this case, we should store some information about this fixed format here. We should have some sort of expert knowledge that tends to be a way of specifying a location. And we could use that then to figure out what it was, that it's a location in this case. We can also maybe learn some useful associations. So there's Chinese followed by powerboat. That might be an interesting association because we don't normally hear about Chinese powerboats, right? So anything, if you're, say, intelligence gathering, Any unusual associations are particularly interesting. Intelligence agencies don't want to hear things they know already. They want to know surprises and things like that that they should get ready for. So this might be interesting. But also you can have associations with any words in the sentence. So for instance, between power won't and leaking, for instance, even though there are 8 words apart there in the sentence, that might be interesting, that particular association. So that's what people do when they do this shallow text processing, try to discover things in text. Here's an example from Google Translate. I typed in some things here to Google Translate. We did a survey, by the way, a few years ago when I was working on translation of file names and file paths on computer systems. And so we had an international collection in all sorts of different languages. So we tested 2 systems, Google Translate and an older system called Systran, which is based on a long history of translation of Russian text. People first started getting into translation methods back in the 50s because there was a critical need during the Cold War to translate a lot of Russian stuff. And those early systems were not very good. So they gradually got better. For a while that discouraged people working at all on translation, but eventually the technology got better and the algorithms got better and the computers got faster, and now we're able to get things like Google Translate that generally give you, for all these things here that I typed in, I got an answer within a second. So that's pretty good for a translation, and they're all adequate Spanish translations. Since I know something about Spanish, they look pretty adequate to me. So for instance, here's Network Security Software Suite. Interestingly though, Network Security Software Suite, it uses the word software rather than programmers here. How does Google do this? Well, it's basically got a lot of matched text. It's got English version of something and a Spanish version of something. And it tries to figure out the mapping between the sections of the text. Usually one sentence maps to one sentence if they are indeed translations. So it gets human translated things and bootstraps on the basis of the human translations of things. And of course, being Google, they have access to billions and billions of web pages, and in those billions there are bound to be translations for 2 languages that it can use and exploit. So use that to get this kind of information here. But it isn't always predictable. It just turned out for this third one here that that it's seen a better translation where software was left unchanged in a Spanish translation. So the Spanish are starting to use English words in some cases. Anyway, purchase our new software. You see it's just added Compre Nuestro Nuevo software. And then some purchase our new Network Security Software Suite. It takes the Software Security Suite thing that we were talking up here and paste that on the back of the stuff that we were using here. So similarly, you can combine it even further, purchase our new Network Security Software Suite in the next month. It has a new prepositional phrase at the end in Spanish here in the same place as in the English. But here's an interesting one, this last one. If you use the word today instead of in the next month, it's smart enough to know that it should put that adverb hoy second in the Spanish. So it's got a more sophisticated thing. So it's actually getting a bit beyond shallow translation, getting more towards what's called transformational grammar, where it knows that in another language it may have to reorder the words in a particular way, and it can learn the way to reorder those words, which is kind of neat. So, as far as translation goes, I should say we tested 35 different languages in this project a while ago, and using Google Translate and this other Systran system. It has much more trouble with Arabic. Arabic has lots of interesting things because often the vowels are missing. There's also a colloquial Arabic, which is not very similar to the formal Arabic. And then there are some interesting problems with punctuation and the fact that characters are drawn differently with calligraphy, depending on where they are in the word and things like that. So with all these problems, I was not too happy with the Arabic translations. But even worse were the Chinese translations. We desperately need some good Chinese translation, but oftentimes the translations I got from Chinese things were total nonsense. And part of that is that you don't know where the words start and end. In traditional Chinese, they just have a whole bunch of characters. You have to guess where the words start and end. There are many different combinations. So there's still work to be done, definitely, on translation systems, even though I like Google Translation for the, Google Translate for the European languages. It works really good for those. For one thing, they're using the same alphabet and stuff like that. So what's the alternative to shallow processing? To do some sort of deeper processing. And so that means we're going to have a full parse and a full semantic interpretation. So I'll show you what a parse means and what semantic interpretation means. We're going to have to also analyze goals and intentions. To understand something, it's often very important to see things that are indirect. So for instance, if somebody asks, could you turn off the light? In English, we know that that is a request to turn off the light. And you shouldn't answer, could you turn off the light, with the answer yes, right? Because that would not be the intention of what was said. So there's a whole bunch of things called speech acts that you have to understand when you see conversation or you participate in a conversation that you're going to have to do in a deeper understanding. Comes from linguistics. There's a big area of human knowledge called linguistics that's analyzed different languages. You need this deep understanding whenever when the exact content matters, and legal reasoning is one example of that. There's a big area of AI that deals with legal reasoning and tries to interpret things there as a way to aid lawyers in trying to prepare cases. My feeling is that deep methods will eventually surpass the shallow methods. You heard Professor Kolsch talk about image processing. Image processing is limited by the huge amount of data, and that's why progress has been slow compared to some other areas of AI, even though they made some great progress recently with convolutional neural nets and things like that. But language is actually a smaller target. Typical language has 40,000 words or so, or 50,000 words. That's usually all you need to converse in any given language. And languages don't change that much, whereas image processing, there can always be new things to see and stuff like that. There's so much variety in the visual world. So my feeling is that this area, natural language processing, is going to get solved completely in a deep way faster than image processing is going to be solved in a deep way. So we will see as to how long it's going to take. You heard in some of the previous talks about people that predicted unwisely about when things were going to occur in AI. So I'm thinking, it's going to be at least 20 years or maybe 50 years before we get really good solution to natural language processing. Here's an example of a deeper analysis of the powerboat example. So here's the powerboat, and this is interpreted as a sentence. This is the parse tree for this. And so it's basically a binary tree, if you're familiar with this terminology here. We got a sentence here which starts with a noun group, which consists of just a noun, and that's the word powerboat here. Then we've got a verb group, which corresponds to this word reported here. It's also got some modifiers on it, a prepositional phrase, two prepositional phrases, and a participial phrase there. But it does have a verb in it there for the verb reported there. Prepositional phrases, here's one at 30 north, 170 east. Then there's another prepositional phrase also using an at, but this at, it means differently. It means basically a time. And then there's also an at here, at 20 knots. That's used to indicate some property of the heading, the way in which the ship is heading. So all those things. But as far as the parse tree goes, this is going to be the structure. It tells you what the general categories of the words are, what are called parts of speech in English. So you're going to need that for deep understanding. You're also going to need a semantic interpretation. So here's my semantic interpretation. This looks like a graph structure. You've got or a network structure. You've got things that are connected to other things in a non-hierarchical way. So we've got a B here, which is a kind of powerboat. And then we've got an R, which is a kind of reporting action. We got an S, which is a speed. We got an L, which is a location. We got a D that's a direction. We also got a time here that are all hanging off the R. Typically in English sentences, well, also in most languages, the verb is the important thing. So everything is most of the things are attached, in this case, the reported word you are attached to that word of the verb, and help explain how it's being used or what other details of how the reporting is taking place. So you see, we basically construct a structure of this. And so what we can do is, if we're trying to match something in a Google-style search, we could construct a parse tree and a little graph structure for the thing we're looking for, and then match it to this graph structure. And if we can match the little graph structure to parts of this graph structure, we've got a match. And so that could be the basis of an improved version of Google search. And people have been working on that for quite a while. But it's a difficult task to do that in general with all the different words in English. But anyway, so that's your semantic structure. That's your semantics. You try to come up with that. Try to have a program that comes up with that. Then discourse analysis. If you got a second sentence here, nearest port is base 83 but is not a full maintenance facility, we're going to need to know that it means the port here. It's this word it, in other words. That's what's known as anaphoric reference. Pronouns like the word it, you're going to have to look backwards to find the most recent thing you mentioned that could possibly be referred to by that structure there. But in some cases it gets complicated. You can also have noun groups and nouns in English that are somewhat vague that you have to do anaphoric reference on too. We also have to infer the power boat is in trouble. So it just says leaking oil, doesn't say anything about the boat being in trouble. So we'd have to have some world knowledge that says if you have a vehicle with an engine that needs oil to run, if it's leaking that oil, that's going to cause some terrible problems down the road. Depends on how fast it's leaking oil, though. So how do we get that knowledge? We need experts, human experts, basically, to give us this knowledge. So that's going to be the basic challenge. You know, even though expert systems have not worked in certain areas, for this linguistic stuff, you definitely need to have some human experts that would just tell you all these little details of the world that are necessary to make some sense of how the second sentence relates to this first sentence here. There's been a number of projects over the years, like there's something called the CYC project, CYC project, still continuing after 20 years in many different forms, which is just trying to codify all of human knowledge that you might need for understanding everyday sort of knowledge. Not even trying to explain complicated things, just the everyday common sense knowledge that everybody has, so you can understand what these sentences are trying to say. You'd also need to know it needs maintenance, right? When you're leaking oil, it needs maintenance, right? And you have to know where maintenance can be obtained for a ship or a boat. So it's going to have to go to some port to do that. Also, you need to know that leaking oil depletes the ship functionality. It needs to be fixed soon. There's a certain degree of urgency about that. So all those are world knowledge that you're going to need to do discourse analysis here. So here are some of the key problems in natural language. It's obviously a noisy signal. It's going to require some guesses and use of context to decipher the signal. The same word can serve multiple grammatical functions. You're going to have to figure out what part of speech it is so you can build that parse tree in general. But even if you're just doing a shallow analysis, you can get much better performance if you can guess what the part of speech is for each of the words involved. There is something called part of speech taggers, which are pretty good at this point, that are able to do that if you've got a full sentence. But if you just type something into Google doesn't often understand what how those words relate to one another and can't exploit that. Then words can have multiple meanings, even when you know what part of speech it is and then it's a noun. There are many different meanings. If you look in a dictionary, a typical entry in the dictionary has 4 different meanings. And so one of the big challenges in deep understanding is trying to figure out which of those meanings it is. So for instance, a word like suit, can mean all sorts of different things. It can mean a lawsuit, it can mean an item of clothing, it can mean a suit in a card game, all sorts of different types of things. And you're going to need to figure those out. All those have accumulated in a natural language over the centuries as the language has been used by people, and you're going to have to figure those out. Then you're going to need to know how the words relate to one another. I did a language understanding system 15 years ago for the captions at the China Lake Air Warfare Center. And so they had lots of different words in those captions. And so I had to define all the different ways that the words could relate to one another. In particular, in English, we have problems with nouns in succession. English likes to have lots of nouns in succession. And so when you got two nouns, my system from 15 years ago had about 100 different ways that two nouns could relate to one another. One could be an instance of the other, one could be a super concept of the other, one could be a part of the other, one could be a whole of the other, one could be related as an instrument of some action, one could be related to time, could be related to location. There were just 100 different ways in which two nouns can relate to one another, and you've got to figure those out if you're going to do deep understanding. Also, prepositions in English are a problem. You saw that example. I used at 3 times, and each of the 3 times had a different meaning. So I mentioned anaphoric references. Also, you're going to need to know theories of causation, how things can cause other things. So that's expert knowledge, as I say, again, to do that. You need to know something about arguments and how arguments, and I mean by argument, trying to convince somebody of something. So often you find in text somebody is trying to explain something or give a reason for something, and you need to understand argument sense. And then you need to know these social interactions between people. There's a whole theory of how people interact that you need to do to understand a conversation or understand when you're reading a report of people communicating what happened there. People do expect high accuracy in natural language conversations. So if you're having a conversation and somebody misses 1 out of 20 words, it becomes difficult to communicate with people. So that's been one of the limitations on using speech understanding systems for a while. Now we're getting to the point where if you can limit the number of words somebody could say, you can get pretty good performance, and you can get 99% performance on all those things. So things are looking up as far as the accuracy. But as far as trying to handle totally unrestricted English with 20 words in a sentence, that takes a while. I was working on systems 15 years ago with 20 words in a sentence. It would take hours just to do one 20-word sentence. Now we've gotten it down to minutes on some of those sentences, but it's still not fast enough to really get useful systems in many cases with longer, unrestricted vocabularies in natural language processing. Okay, that's all I wanted to say. Any questions?